All right, welcome everybody. I'm super excited to have this discussion with you all. So just some background. I have been building agents both inside the company, outside of the company for almost a year now, and built many iterations and incarnations of these things. And I've learned a lot from the process, and it turns out that it's difficult, but also easy if you have the right abstraction. And so I wanted to share some of the learnings here. And to start off, the general provocation or idea is that we want to build agents. We want to build agents as our products. We want to build internal agents. Along the bottom here, you may recognize some logos. At this point, pretty much all of the LLM providers are effectively agents. And we don't just want to build them from a proof of concept hackathon perspective. We want to build them with proper production principles, meaning we want to know that they're working well. We want to ensure that they have proper security guarantees that have been designed up front. We want to be able to observe these agents as they actually unroll or execute in production. We want to be able to test these agents, meaning as the agents make steps through their iteration, we want to ensure that everything actually works correctly. There's a number of other things, including scalability and things like that. So we want to take the same mindset that we have when we build production systems at GoGuardian and basically apply them to agents. And it turns out that this is actually challenging to do. Most interestingly, because I think all of the agent SDKs out there, and I've used many of them, pretty much all of them have a fatal flaw or many fatal flaws. And in my view, don't provide the core abstractions necessary to build good, reliable agentic systems. So here's a code block over here. This is using the OpenAI agent SDK. Pretty much all of them more or less look very similar here. So here we're constructing some agent class. And then this is a post handler. A request comes in. We're indicating that we want to run the agent with streaming here. And then we use this generator to process the events one by one, essentially. And then finally, we're accumulating all of the events as they come in. And then finally, when the whole turn or invocation succeeds, we want to actually return that as a response. So if you look at most agent SDK websites, this is roughly the structure that they suggest. But I think that there's actually quite a number of problems here. And so the first problem here you'll notice is that this agent run is effectively bound to a HTTP request context, meaning when the user actually reloads the page midstream, that context goes away, and we effectively lose the run. Relatedly, we probably want to actually store the results of this agent run somewhere so that we can refer to it at some point later. And so this begs the question, like, how do we actually serialize and store the agent state? Do we, for example, on line 15 here, persist all of the incoming events, or do we wait until line 19 where the run is complete, where we persist the entire state? It's not exactly clear the approach that we should take and the various pros and cons. And then how do we stream this to multiple browser tabs? So if a user has multiple tabs open, or in some instances, if there's multiple users looking at the same session in a multiplayer context, how do we ensure that each user is ultimately seeing the same agent run? And how do we handle that in situations where we have high latency networks or networks that actually drop? In this particular like hello world agent structure, like we can't easily do that. Now, you might say, well, sure we can. We can basically come up with some pub sub mechanism, and then we can use WebSockets per client, and then we can push events through these WebSockets. And and very quickly you start to realize that as you do this and consider durability and multiple clients and things like that, the hello world example kind of goes out the window. And in my experience, what ends up happening is we end up cutting corners where we make design decisions that inadvertently compromise on things like durability or user experience. And I think that this happens because the core abstraction that these SDKs are providing is dissatisfactory or not aligned with the thing that we're ultimately trying to represent. And so another consideration here is like what actually happens when we deploy a new app version midstream, or if we're running on an EC2 instance and the EC2 instance blows up, right? In most agent implementations, basically the result is that we just show an error to the user and it's up to the user to retry, right? So again, dissatisfactory UX in my mind. And if you think about these things like durability, multi-client sync, like application restarts midstreams, high latency networks, all of these things seem like challenging problems, but it turns out there's actually a very clean abstraction that if we implement our agents in this way, it allows us to address all of these concerns in a very systematic way. And so we'll get to that abstraction, but I wanted to provide this as the motivating example for the problem that we're ultimately trying to solve as we build these production agents. Okay, so before we get to the solution, let's deconstruct the agent a little bit. This is a Claude code session or a Claude web session where I basically just asked it, please explain how the agent loop works, make some tool calls, and then provide a concise explanation. And so it thinks for a little bit, it runs these tool calls, and then it provides the actual result over here. And so deconstructing this a little bit, this is the user message, usually provided in the form of user input somehow. This is what's known as a reasoning message, sometimes also known as a thinking message. The idea here is that behind the scenes, there's actually a bunch of reasoning tokens that the LLM provider generates. And most LLM providers, to the extent that their proprietary models actually encrypt these reasoning tokens. So when we receive the reasoning blocks, we don't get the actual raw reasoning tokens. Instead, we get an encrypted blob paired with oftentimes I don't know, single line summary that summarizes the thinking block. So in this case, the summary is, I'll search for current information on how agent loops work and then explain. Next here, we have the actual tool calls. We'll get to the actual structure of tool calls, but here you can roughly imagine that to this Claude agent is exposed a tool that's like a web search tool where the agent can request web searches. Then those web searches are actually ultimately fulfilled somehow. And then finally, we have the assistant message, which is typically the final message. But oftentimes these reasoning messages, tool calls, and assistant messages are interspersed. And you can get many of them in different patterns and different orders. And so this is essentially the atomic units of an agent run, essentially. Visualized slightly differently, we have the context, which is the input that goes into the LLM. And then the LLM is able to produce these three things that we've been talking about: tool calls, reasoning messages, and assistant messages. And then the agent harness, which is to say the outer structure that's responsible for driving the agent loop, is ultimately responsible for actually executing these tool calls and producing tool call results. These tool call results, alongside the tool calls, the reasoning messages, and the assistant messages, are taken all together, packaged, appended to the actual context, and the process essentially continues in the form of a loop. And so this is the agent loop that everyone should be familiar with by now. This process continues until some stopping criteria, usually the LLM itself determining that, hey, I'm done, I no longer need to execute. And the final output is ultimately just an assistant message lacking any tool calls, signaling to the agent harness that we're done with the run over here. So just from a terminology perspective, we have the agent turn. This is just a single turn, which corresponds to a single LLM call. And the output of a single LLM call is all of these blocks over here. And then this creates a loop, and then as the loop executes multiple times all the way up until final termination, we actually call that an an agent run. So you have a turn, which is just a single LLM invocation, and then you have a run, which is a sequence of LLM invocations that ultimately results in a final stopping condition. So those are the terms. Okay, so now we get to the actual solution here. It turns out that it's actually useful to model these agents as state machines. State machines are really, really cool abstraction. If you haven't heard of them before, I'm jealous because I think you'll be mind blown a little bit. Ultimately, a state machine can be reduced to this structure over here, where given an input state plus an event that comes in, the state machine function, or reducer function is often what it's called, is responsible for producing the next state as well as a set of actions that need to be executed. And the important idea here is that this reducer function is a pure function, meaning it doesn't actually perform the actions, instead just describes what the actions are that need to be executed. And ultimately, like, modeling the whole agent as a state machine distills like a very complicated structure into actually a very, very simple construct. And so how can this be? Why is it simple? It's simple because firstly, there's no actual imperative modifications happening anywhere. So at no point are you doing like a array.append or a WebSocket write or anything like that. Instead, based on the state and based on the event, we're producing a new state. We're not modifying an old state. And this is, of course, you may recall, very similar to like the Redux abstraction over here, where on the front end, we get a very similar problem, which is we have some state within our application, and the user is oftentimes performing a bunch of interactions on the page, or you have a fetch that happens, maybe it starts and maybe that finishes and maybe that it errors. And all of these events ultimately have an influence or an impact on the state. And before the React era, before the Redux era, if you recall the jQuery era, like the way that we were managing all of this state was really, really chaotic and not principled, let's say. And so came React and then Redux, and we kind of forced the whole UI interaction structure into this mechanism, which is the reducer, and everyone knows firsthand, hopefully, like the net result in terms of simplicity. And so very similar to that abstraction for the front end, we can actually apply the same abstraction to model these agents. And so given a state and various events that can happen, we provide the next state and the next set of actions. Okay, so what is this state that I keep talking about? I think you can actually bifurcate the state into two categories. The first is durable state, and the second is ephemeral state. So durable state usually corresponds to state that gets serialized to disk or some database somewhere, such that if there's ever some process restart or whatever, the durable state is ultimately persisted. Whereas the in-flight state is in memory and by definition lost in the event of a process restart. And so for the durable state, we have things like the system message. We didn't actually discuss this one in specific, but you can imagine it's a message that's prepended to the context before any other messages come in. And that defines the general behavior of the agent system, like who the agent is, what persona that it's supposed to have, what it's supposed to do and not do, and so on and so forth. We also have user messages. We have assistant messages, tool calls, and tool call results. And then you have this in-flight state, which is oftentimes actual like promises in flight or JS closures in the form of the actual LLM inference stream, or actually any tool calls that might be mid-execution and things like that. And so what we can do is bifurcate the state and in this state machine construct, basically say, okay, if I have the context and I have an event comes in, like for example, a user message was submitted, what am I supposed to do? Well, first thing I want to do is append the user message to the user messages array. And then I want to actually store that state durably. And then maybe in some instances, I want to actually kick off an LLM call. But I don't want to always kick off an LLM call because maybe I'm actually midstream and maybe instead I want to actually queue the message instead. And you'll see based on this example that just by virtue of forcing us to construct the agent as a state machine, it actually forces us to reconcile all of the various states that we might be in when an incoming event actually happens, and then actually model the desired outcome of the system in a much more systematic way than maybe what we're traditionally used to in the original motivating example, where here it's not exactly clear what we should do given an event that actually comes into the system. Okay, continuing onwards. Here in this LLM loop, all we have to do is, as each of these steps actually execute, we simply emit these events. And this is a rough archaeology of the various event types. Each row corresponds to a category. And then this middle column here describes the different event types for that category. And so for user messages, you can imagine an event that's like user message committed. For an actual run, which is the beginning of a sequence of turns, you can imagine a run started event. For a turn, you can imagine a turn started, but then also we're proposing an actual turn failed event over here, effectively describing very explicitly when the LLM turn actually fails and representing that as a formal event within the system. And then you can imagine that turn failed event also can contain some metadata about what the nature of the failure was. Was it a network error? Was it a model error? Things like that. Similarly, you have assistant messages. So you have an assistant message started event, which indicates that the streaming of the assistant message has begun. And then secondarily, you have an assistant message committed event, which is, okay, the streaming is done, and now the full contents of that assistant message are available and represented concretely in the assistant message committed event. And so hopefully you start to get the idea. We've basically taken the entire loop here and we've outfitted every start point, end point, and failure point with an actual event that gets emitted. Then what we do to these events is that we actually sequence them, meaning when an event actually gets emitted, we number that event in a centralized way such that each event follows the next event in number. So monotonically increasing is the technical term for this. And then by doing this, we actually get a few pretty incredible magical properties. The first property is that the event log or the event stream over here basically authoritatively and fully represents the entire history of the state machine. So event 1 represents the very first event, and then event 2 represents a state transition from state 1 to state 2, and then event 3 represents the next state transition, and so on and so on and so forth, right? And so these events effectively become your storage strategy. So when you're trying to serialize a state to disk, instead of figuring out what your serialization strategy should be, you can actually just simply store the events in sequence. And then when your process restarts and you need to rehydrate the state, all you do is read these events one by one and apply them using your reducer function. And the output, the final state that results, is the actual final state. The next thing that this system provides is multi-client sync, where if you have multiple browser tabs that are open or multiple consumers in general, each consumer can basically keep track of its sequence number, which is which event in the stream has it actually received. And then even if you're dealing with flaky network connections or high latency network connections, you have this property of eventual consistency, where eventually as these clients catch up and receive the final event, then they will have ultimately caught up to the rest of the clients, and all of the clients are ultimately in sync. And so midstream, if that client disconnects for whatever reason, it keeps track locally of which events that it has read up to. So let's say it has received event 1, event 2, event 3, and then a disconnect happens. When that client reloads, it starts saying, hey, I have event 3, please give me all of the events after event 3. And then the backend will essentially stream event 4 all the way to event n. And then as soon as it receives these events, that local client will apply the same reducer function and effectively rehydrate the same state that everyone else is seeing. So this is a pretty magical property. This is the same exact property that's used effectively in databases in the form of the write-ahead log or the leader-follower replication log, where if I have a leader database and then I have a follower database instance, it's critical that eventually, once the follower has received all of the events and caught up to the event stream, that the state of the follower is exactly the same state as the leader. Meaning any query that I provide to the leader and any query that I provide to the follower should be perfectly equivalent. That's like a critical property of database replication. And it turns out that this is the exact same mechanism that we're using in our system, but instead of replicating a database, we're effectively replicating the state of an agent across multiple clients. This property is also the same structure as queuing systems like Kafka, where Kafka effectively manages these sequence numbers on behalf of the application and is really deliberate about maintaining the ordered log of events. And then Kafka provides a mechanism for readers to basically independently have different cursors on this event stream with the property of leaders eventually catch up, followers eventually catch up, and once they've caught up, then they have the final state. So we're sort of borrowing these ideas from database design or just general eventual consistency, and we're applying them in this construct. And then finally, like this structure lends itself very, very nicely to observability. So observability has many dimensions. My favorite aspect of this is what's the word for it? It's like time travel debugging. So if I have a bug in my application or in my agent, and I'm trying to figure out like what actually went wrong, what I can do is go back in time and apply each event one by one and look at the actual state. In some instances, if it's a UI application, I can render the UI as a pure function of that state. This is pretty straightforward from like a React perspective. And then notice like when the bug actually happens as I step through each event one by one by one by one. And then eventually, once I realize there's an issue, I can actually fix that issue like then and there. So simply by having the sequence of events, we can go back in time at any moment, see what the UI looked like in that moment, and then fix an actual issue. This observability is also useful for things like logging. So if I have a production system trying to figure out like what actually happened, why did it break? If I simply just log these events, maybe stripped of PII or other sensitive information, then I get a really nice trace of what actually happened in this agentic system. Okay, shifting gears a little bit, I want to now talk about tool calls. So tool calls are effectively the interface between your agent and the outside world. And if you look on the left here, the code basically describes a tool. The tool definition here is called run bash, run a bash command, pretty simple. It has a simple single parameter, which is the command that actually needs to get executed. And then you have an execution function, which actually fulfills the tool call. And so whenever this agent runs and the LLM decides that it wants to call the run bash tool, it constructs a payload that conforms to this actual schema over here. And then the agent harness will call this execute function with the actual parameters here bound based on what the LLM actually wanted to provide, right? And then the execute function happens, and then we take the result, which in this case might be a summary of the actual outcome. Maybe it's standard out, standard error, exit code, time, stuff like that. That tool call result then gets serialized as a JSON blob and then gets passed back into the LLM, where the LLM now has visibility into the execution of the tool call and then can decide itself whether it wants to continue with more turns or whether it wants to actually end over here. And so if you notice, there's actually a critical fatal flaw here in this structure, which is that the way that the run bash tool is being fulfilled here is by using the child process exec facility from within Node, right? This is actually really, really catastrophic and effectively is the actual mechanism behind agent harnesses like OpenClaw or all local coding agents, more or less. And the fatal flaw here is that the host environment where this application happens to be running in is a sensitive, privileged environment. It might have within the ambient environment, for example, a file system. Maybe it's your actual local MacBook. It's got a bunch of stuff there. Even if it doesn't have a file system, maybe it has access to a local network. Maybe it has access to some local disks. Maybe it has access to some ambient environment variables. You get the idea. And the actual code that's being generated over here, we should consider from a security perspective to be effectively adversarial input, meaning adversarial input in the sense that you should expect a malicious actor to be synthetically generating code here that your system ultimately needs to be resilient to. And so by executing the actual bash command within the ambient host environment, we're effectively giving this adversarial agent free reign on the host machine that the host application happens to be running within, which everyone should feel is absolutely catastrophic from a security perspective. Okay, so what do we do about this? How do we solve this problem? Well, first, a recap. Tools are the interface between the agent and the outside world. The harness itself is responsible for validating the tool call schemas. This usually happens transparently in the form of the agent SDKs. But ultimately, the idea here is that when the LLM produces a tool call JSON payload, it's not guaranteed to actually conform to the schema. So there needs to be a first step where we actually validate that the LLM generated tool call itself conforms to the schema here. And then finally, it's up to the harness to decide how the tool call is actually executed. And this strategy here of using the child process exec is wrong. No one should be doing this. Okay, so how do we solve this problem? In order to solve this problem, there's a really useful idea here, which is separating this notion of the hand and the brain. So we can think of the agent harness or the agent itself as the brain, where the LLM has this reasoning capability and describes an intention to perform a certain action in the form of a tool call. And then we can think of the hand as a separate mechanism that actually fulfills the tool call in a completely independent way from the brain. So the key idea is these two things should be disconnected and separated from each other. This separation is absolutely critical from a security untrusted execution boundary perspective. Also, another dimension of how we can look at this from a security lens is through these levels that I'm calling tool call execution levels. There's not really good standardized terminology for this, but the general idea is relatively simple. When I seek to fulfill a tool call, there's actually many ways that that tool call can be fulfilled. Level 0 here is the simplest, which is not offering any tool calls whatsoever to the agent. So for example, if I'm simply trying to do sentiment classification for an incoming text payload and not really providing any functionality for the agent to make any tool calls whatsoever, then from a security perspective, there's ultimately no risk. Level 1 is when I have this execute command over here, instead of it actually calling node child process exec, instead, you can imagine like a function here that makes a database call, for example, where it's not necessarily an open-ended SQL interface that we're exposing to the actual LLM. Instead, it's actually like a scope, very specific database call that I'm making, where the security isolation is guaranteed by virtue of that interface over there. Meaning, like, let's say I have a database, and within that database, I have a table that describes user information. And I have a tool call that basically says, get current user information. You can imagine the execution of that tool call takes a user ID, not from the actual agent itself, but from some surrounding context. Maybe it's some authorization context where we have dereferenced the actual user. And then the execute function performs a SQL query reading that row bound to that specific user. So in this context, there's no possibility of somehow shoehorning an alternate user ID into the actual fulfillment of that function. That user ID is like hard bound. I'm not sure if that makes sense, but hopefully it does. So we call that level 1 over here, which is the harness itself provides very specific function implementations that allow the harness to govern like what the security boundaries ultimately are. Now, this is useful and effective, but I think level 2 and level 3 is where you start to get to what I would consider to be like real agent capabilities. And what I mean by this is these LLMs are actually incredibly effective and efficient at generating code to perform long horizon tasks. And we need a mechanism to ultimately execute the code that these agents are generating in service of the task, but we need to execute that code in a safe and constrained way. And here there's, I think, 2 gradations. There's level 2 and level 3. Level 2, you can imagine that the code is constrained to a very specific execution runtime. I think the most mature of level 2 ecosystems is essentially JavaScript code that runs in these things called isolates. Isolates you can think of as very lightweight JavaScript containers, effectively, that are hard isolated from maybe the host process's isolate. So the canonical example here is when you're running Google Chrome locally, Google Chrome has support for multiple tabs, and there's really, really hard boundaries between 2 different tabs and the ambient environments of those tabs, meaning I can't just reach over into another tab and grab a local variable. And the way that the Chrome team or the V8 team really has implemented this construct is this thing called a V8 isolate. And you get the benefits of hard isolation, but you don't get really any of the drawbacks of a much more heavyweight system like a full VM. And so the net effect is that within a V8 isolate, I can run untrusted JavaScript code and not have any concerns about what that JavaScript code is capable of doing. So it won't, by definition, have access to the overall host. It won't be able to fork a child process. It won't have access to a file system. It won't necessarily even have access to a network, meaning web fetch will be disabled unless you provide it in a very specific way. And so this level 2 over here is generic JavaScript running within a constrained runtime, oftentimes a V8 isolate. But truly, this expands to different isolated runtimes. So for example, if I have a Python VM that's running somewhere, I can toss some code into that Python VM and execute it. But the point here is that rather than level 3, which is a more general purpose Linux machine that has access to binaries and compilers and stuff like that, level 2 is constrained to just a single like a JavaScript execution, if that makes sense. Okay, that gets us to level 3, which is the maximum power over here. Gia, which is the GoGuardian internal agent, ultimately uses this as the mechanism to fulfill all of its tool calls. This has the most power over here. So it's a full sandbox, a full Linux environment. You can use curl, you can use bash, you can use Z shell, you can use Node, you can use Python, you can use FFmpeg, you can use the Rust compiler. And if the agent doesn't have access to any of these things, you can provide it the capability of downloading these binaries to basically construct whatever execution environment that it actually wants. So we consider this to be like an open-ended execution environment that's maximally powerful, but obviously has its own security risks. So the whole idea here in this slide is that there's a dimension of tool call execution levels. Level 0 is the most safe, level 3 is the least safe, and they're ordered in sequence over here. And each level represents a different mechanism that we can use to fulfill a tool call, which is to say provide a tool call result given some LLM generated tool call input. Is that clear? Okay, so this again begs the question, if LLM generated code for level 2 and level 3 is fundamentally adversarial, how do we actually prevent catastrophic security escalation over here? How do we prevent specifically the leaking of secrets? And then how do we prevent the agent from doing stuff that it's not supposed to do? And so in order to solve this problem, there's actually like 2, I would say, good techniques that have started to emerge. The first is constrained to level 2, and it's a type of access control that's known as capability-based access control. You may have heard of like things like role-based access control. Capability-based access control or object-based access control is like a different flavor of access control where you get access to a certain capability based on having reference to a specific object that's loaded within your environment. And so here on the left over here, I have a host, the host system. And here I have a GitHub repository where I've exposed a method here called create issue. And here within the host, it's a sensitive environment, right? So I have access to some sensitive secret over here. And the actual body of this function, create issue function, basically calls github.issues.create with a title and body, right? And then what I do is within the isolate, I can run some JavaScript where I have this thing called a binding, where this repo variable is actually an ambient variable, which is bound to not exactly this class, but the technical term here is that it's a stub, an RPC stub, such that when I call the RPC stub with repo.createIssue, what actually happens behind the scenes is an RPC happens between the client and the host. And on the host, this body actually gets executed. The result of the body gets then passed back to the client. And all along, the client itself has no ambient access to the actual secret like, at all, right? And so, for example, if I try to do a fetch with this n.github token, there's no n.github token at all in this environment. And then if I even try to introspect this repo construct, all it is just an opaque RPC client or RPC interface that I can't export. So I can't JSON dump it, and then try to exfiltrate it to an external environment. It's simply just not possible. And so using this mechanism of cap and web, which is a capability-based access control mechanism, I can give the client, which is an adversarial environment, access to some privileged capability, which in this case is the ability to create GitHub issues without actually exposing raw secrets to this client. And so you effectively get the best of both worlds, which is lending the agent some capability, but fundamentally preventing that agent from exfiltrating that capability to an environment that's outside of this client environment. So hopefully that makes sense and that's clear. Okay, the second mechanism, which is starting to become popular as well, is man-in-the-middle secret injection on the wire. And the idea here is that rather than so for cap and web, this L2, this mechanism is limited really to level 2 environments, which is these lightweight runtime environments. If we want to protect level 3 environments, really, I think this is the best, perhaps only mechanism to do this, which is when we actually create a sandbox, what we do is we associate that sandbox with a man-in-the-middle proxy credential injection policy, let's say. And so what that means is we're indicating to the sandbox, hey, I'm providing you this secret called a GitHub token, and it's only accessible for HTTP requests to this specific host, which is api.github.com. And then the value is this actual end.github token, which in this case is the secret, because again, this is a host, so it's a privileged environment. And then I want to do sandbox.eval agent bash code. And this might run a curl. It might write a Python script which performs a bunch of HTTP requests. It might spin up a node environment, which also does a bunch of HTTP requests. Regardless of the mechanism, ultimately, the sandbox performs some HTTP requests somehow. And the sandbox is pre-configured with an actual proxy that conforms to this policy, such that when the request goes out on the wire itself, there's an actual swap of the credential, such that within the actual client, the client is never exposed to the raw secret. Instead, the client only has access to a placeholder stub value. So to make this a little bit more concrete, let's say we have this token, which is the process.end.github token, and we try to log this token. What's actually logged is just an opaque placeholder string over here. But when I make a fetch to api.github.com with a set of headers here, in this case, the authorization header providing a bearer token with this placeholder, the man-in-the-middle proxy basically intercepts that outbound requests, sees this placeholder GitHub token, swaps it out with the real token, and then sends a request along the way. And so with this mechanism, the client now has this capability of performing HTTP requests to this particular domain while never fundamentally having access to the underlying secret that was necessary to successfully perform the actual API request. And so as a result, again, we have provided the agent this capability while fundamentally, from a security perspective, preventing the agent from actually having access to this proxy. Now, important consideration over here, the proxy itself can't run on the sandbox co-located with the agent environment because to the extent that the agent has the ability to generate arbitrary bash code, you don't want it to be able to poke at the proxy, look at the actual values, maybe disable the proxy somehow. Instead, the proxy needs to live at a separate layer such that any outbound request from the sandbox to the outbound internet is always and fundamentally hijacked by that proxy. And it turns out that some sandbox providers, particularly Dino Sandbox, which is the mechanism that Gia uses to actually fulfill all of its sandbox work, Dino Sandbox provides this built-in proxy mechanism where they host the proxy for you. They manage like all of the secrets here. They manage like the binding of the sandbox to the proxy at the network layer. They manage the certificates for you so that the man-in-the-middle injection can work successfully. All that happens transparently for you. But in principle, you can construct this system yourself relatively straightforwardly. All it requires is just some man-in-the-middle proxy and some hard mechanism such that all outbound requests from the sandbox get funneled through this proxy. And so this man-in-the-middle secret injection is a pretty solid way to ensure that you don't fundamentally prevent secret exfiltration. And it works for both level 2 and level 3 tool call execution mechanisms. So we have this lightweight JS runtime. You can imagine you're doing man-in-the-middle secret injection with that, or you have a full sandbox and you could similarly do man-in-the-middle injection that way as well. This is a great stopping point because this is actually the end. So Chris, you're just in time. Maybe we'll turn it over to everyone for questions.
Perfect. So I've got a question about this man-in-the-middle injection pattern. You said that the outbound responses are intercepted. What about the replies? Are the like inbound replies also intercepted in case, you know, say a different token gets set in a response header? Can we make sure that we're stripping those out as well to not leak other secrets?
Yeah, it's a great question. So in this particular example, the answer is no, meaning like the facility that Dino Sandbox specifically has provided for us here, we're not actually taking the responses and doing anything with it. But the broader answer is we have the freedom to design whatever system that we want. And if we want to, for our needs, actually take all of the responses that are coming in, maybe log them, strip them of tokens, double, triple check that this secret over here does not actually appear in the response, or maybe any secret pattern whatsoever doesn't appear in the response. We can strip that at the wire level, at the proxy level, such that the response that's returned back to the sandbox is sanitized. So we have that flexibility. Ultimately, it depends on the nature of the application and the specific risks that we're trying to mitigate. But it's a good question. Great. So feel free to jump in with other questions. Hopefully, you see the arc over here. That if I were to briefly summarize, it's represent these agents as state machines such that you have a durable event log. This durable event log can then be streamed to multiple clients. In addition, as you represent tool calls, think very critically about this hand in the brain structure, such that the hand is fundamentally isolated from the brain as you go about executing these tool calls. Then for the various hand implementation structures, think about the various execution levels that you might want or need based on your application, and pick the most limited one that suffices for your particular application. And if you want to do level 2 and level 3, to the extent that you want to provide the agent some capability, you need a reliable mechanism to provide that capability without risk for secret exfiltration. And with that, you have two solutions, one being Captain Web and one being MITM secret injection. And I think with that, you have a pretty solid foundation for building these agents that have all of these properties that we care about from a security perspective and a reliability perspective and so on. So back over to you, Chris.
Yeah, and I agree. I think this is a really strong foundation for all of this work. One question I had, which going back to earlier in the presentation, you were discussing that it wasn't anything that I'd been thinking of before. That a lot of these sessions are multiplayer sessions where there are different actors involved. Do we have any way to to make sure that, I think if we're operating, in a capability based access control, if some elevated user, starts up the session and non-privileged user then accesses this, just by nature of being in that conversation, there's going to be data exposure, and I don't think that's solvable without a completely different system. But is there, does RBAC appear anywhere such that if the non-privileged user then is like, oh hey, I want to send a command or a prompt, does it then still run with the same elevated capabilities that the person who initiated the session had? I'm just trying to figure out, is there something that we need to do, to make sure, hey, you're not sharing certain sessions with certain people, that sort of thing.
Yeah, it's fantastic provocation. So I'll answer this first generally, and then I'll answer this in specific with regards to Gia and how Gia thinks about this. So generally, your provocation is absolutely correct. To the extent that we're supporting multiplayer sessions, which I think is a useful feature. You can imagine in the context of GoGuardian, we want to build an agent that's exposed to our users, where inside of GoGuardian admin, we want an admin to be able to ask questions like, why is my filtering policy not working for this particular student, right? In order for an agent to usefully solve that problem, it needs to ultimately make capability-based API requests that are bound to some capability authority, let's say, right? The most natural one is, let's just inherit the authority of the user that triggered the session to begin with, right? But then if we want to then subsequently layer on multiplayer, meaning that same session, perhaps we want that admin to be able to send to one of their colleagues, or to maybe someone like a student, or perhaps an internal support rep, right? And then any of those users, if they send a request to the same session, it really begs the question, like, how do we think about the capability of that second request? Does it ultimately inherit the capability of the original instigating user? Or does every request basically have a different flavor or level of capability based on the user that sent the message? I don't think that there's actually a universal answer. I think really we have to think about the nature of the product and the nature of the risks, and ultimately design a policy that makes sense for the case in hand. So that, I think, is the general answer, which is to say that you just need to think about this critically and realize that as soon as you are exposing this multiplayer construct, that you have different types of principles, and different principles might have different capability levels, and you need some policy to ultimately determine what the final resolved capability set needs to be. Now for Gia in particular, so Gia has a web interface, and Gia has a Slack interface. The Slack interface is necessarily multiplayer, meaning we want to encourage people to start a Slack session and ask questions to Gia, and then have other people follow up. We're seeing a lot of use of just the shared Slack thread as a mechanism for sharing information internally within the organization. And so to the extent that Gia has user scope integrations bound to highly sensitive privileges, particularly things like Google Drive, or eventually, for example, the ability to make a production deploy or merge a pull request. These are extremely sensitive operations. We don't want those capabilities to sort of leak out in the form of a Slack thread, where now all of a sudden some other de-escalated low privilege user now transparently has the ability to escalate their privilege somehow. We absolutely don't want that. So the design decision in Gia, what we decided to do was ultimately, for all Slack conversations that are ultimately multiplayer, we prevent all, from the beginning, user-bound privileges like whatsoever. So the only way to have a user-bound privilege is within the web UI, where we can have much stronger guarantees about the single player nature, multiplayer nature of the session. in a Slack context, we've just said, we're not going to be able to reconcile this. We're just turning off all user bound privileges, which is an inconvenience, sure, but ultimately it guarantees the sort of security isolation that we absolutely need as Gia has access to more and more secure and sensitive capabilities. So coming back to the web sessions, we do support multiplayer, but the way that this is solved in Gia is we have two flavors of sessions. There's either a public session or a private session, similar perhaps to Google Docs, but it's different than Google Docs, where public sessions are always just view only, where it's the responsibility of the person who's sharing the session to ultimately make sure that whatever is contained within the session doesn't actually expose any sensitive information. And I think they can make that determination because ultimately they're also making similar determinations as they use Google Docs and share Google Docs and so on and so forth ordinarily. And then when that session is shared and another person views that session is ultimately view only within the web interface. So there's no capability for that second user to send a message on behalf of the first user. Now, this is a policy decision. We can ultimately decide that that's a wrong policy and that we do want that second user to be able to take actions, but those actions should be bound to a separate and different capability scope than the first user. That is a valid structure, but that's a structure we decided not to go with because of the natural complexities that arise with those kinds of capability delineations.
Yeah, I was going to say, yeah, some of the people at my university, my comp sci program actually did some of their thesis and dissertation work where it was on using lattices to help determine who could have access to what information. We did a lot of work with the DoD, and so in classified networks with different sensitivity levels, there was a lot of work that could be done to help prevent access to information like that. But yeah, the scope of that is incredibly complex. I think the model of delegate letting the person who's initiated the conversation delegate their session to someone else, they can do the due diligence to say yes, everything in here is fine. And especially if like you said, it's read only right now, that's perfect. That's a really hard line that we can easily draw and deal with if we want to have multiplayer input sessions in the future. So awesome.
Absolutely.
No, I love it.
Great provocation. Thank you. Go ahead, Vishal.
Yeah, so thanks firstly for the session, Advait, and sharing the learnings as well as the things you've learned from building Gia. One question on the sort of on the level of the tool calls, you mentioned Gia is sort of level 3. Do you envision I guess when one was doing something for the customers, like how are you thinking between, because again there is trade-offs between the different levels. And so is it because Gia is an internal tool? Do you see any use cases where it might be a combination of, in general, level 3, but also some being level 2? Or when we do it for a customer, what do you envision in terms of the right tool call execution level?
Yeah, so I'll share a blog post that was by the Mintlify team. Mintlify, if you guys don't know, is a support content management system product where most of the modern companies like Anthropic and so on, when they build help centers, they run them on Mintlify. So it allows you to represent articles in Markdown format, and then it renders those articles like a CMS would. But interestingly, they support an agent interface to their product. And so they have this similar question, which is, as a user asks a question to this agent, and we ultimately want this agent to be able to read and reference the various support articles within the ecosystem, how do we actually fulfill this in the most cost-efficient way, in the most latency-efficient way, but also in a way that hopefully doesn't compromise on quality and capability? And so the particular structure that they honed in on was, they originally started with level 3 and very quickly discovered a lot of drawbacks associated with level 3. I think the most prominent ones of level 3 are cold start latency. So when you spin up some of these sandboxes, it's getting pretty fast these days, but you should budget somewhere around 200 milliseconds, maybe 500 milliseconds, 95th percentile cold start latency, which is relatively significant if you're in an interactive context, right? But I think the other issue is actually around cost, where simply these sandboxes are spun up, they're sitting around, they're consuming 1 or 2 cores, maybe a non-trivial amount of RAM. You're getting billed for those things, right? And so as you scale these agents out to prospectively millions of users, you're very much incurring a compute cost associated with that. And so what they decided to do was re-architect their system to a level 2 system, where they use a very similar structure here. I'm not sure whether they use this particular library, but they have a capability-based model and expose the ability to search for articles, read articles, and the various actions that you might take within Mitlify in the form of tool calls within a JS context. And this is different than, I think, tool calls as I'm talking about here, right? So this is a agent-facing tool call. What I'm instead describing here is within the isolate, a function that when that function is executed actually performs the tool call, right? That's very different because it actually allows the agent to generate code to, for example, make in batch 50 tool calls looking for various strings. And then once that results, then making again in batch a bunch of tool calls to read a small subset of the articles that were returned, right? You can imagine the JavaScript that represents that parallelization, and that parallelization I think is critical to a high performance system, as opposed to if you're limited to the original tool call construct over here, the agent can only generate these tool calls serially, one by one by one by one. So it actually stacks up from a latency perspective. And so Mitlify honed in on their solution, essentially using this L2 system. And I think it's the balance, like best of both worlds, where cold start latency for these V8 isolates is basically single-digit milliseconds. So a rounding error relative to overall LLM latency. The costs are relatively small, and yet you get the performance. Sorry, you get the capability of authoring open-ended JavaScript to orchestrate arbitrary workflows of arbitrary complexity to perform certain tasks, while also being limited in the capability context, like in all the ways that I'm describing. So net, I would guide us towards level 2 over here, perhaps starting, frankly, with level 1 as a proof of concept, because ultimately everything in level 2 can effectively be represented in the form of level 1, albeit just in a serial way, meaning the LLM can generate one tool call at a time. But in the process, you can prove that the structure actually works, and then you can have very hard guarantees around things like data exfiltration as a result. But then if we maybe tap out on the total number of tool calls, so you can imagine the GG admin API surface area to easily be 50, maybe 100 various tool calls, and then you layer on all of the other products, you can imagine a world where we have thousands of prospective tools. I think for that environment, thousands of tools is far too many to cram into a single LLM invocation. And then at that point, you have to resort to level 2 with more of like a progressive disclosure strategy, where you provide maybe a tool for the LLM to search for all of the tools that are available. So just a search tool, right? Which returns a bunch of tool interfaces, which then can be used to, again, by generating JavaScript to actually execute those tools to perform some certain work. So net, start with level 1, maybe graduate to level 2 if level 1 becomes a constraint, but absolutely do not move to level 3 for user-facing products, because I think that we're going to we're just cost limited, frankly, and latency limited too, which I think is a critical factor.
Thanks.
Great. Anyone else? Okay. I think with that, we're good to wrap. I had a lot of fun with this. I think we're very much entering into the agent era. And I hope this was useful, interesting to you all. As you go about building agents within your products, I'd love to have a conversation with you. There's actually many, many more things that I didn't cover here that are important considerations when thinking about building production agents. So whenever you all are sort of scoping the work or thinking about design, thinking about implementation, feel free to send me a Slack. I'd love to have a discussion and share more of the learnings. With that, I think we're good to wrap up. Thanks, everybody.